Hey everybody, welcome back. We're going to continue with chapter 4. We're going to talk about the octet rule, the sign and magnitude of ion charges and isoelectric species. And this corresponds to sections 4.3 and 4.5 of your text. We'll also revisit section 4.4. We talked about what makes up an ionic bond earlier in chapter 4, but we'll revisit that during this section as well. So again, our two fundamental concepts of bonding. The first is that not all electrons in an atom participate in bonding. The electrons that do participate in bonding are called the valence electrons. And that's what we talked about in the previous lectures, how to figure out the number of valence electrons based on either the location of an element of the periodic table. You can use the periodic table method and the Roman numerals for main group elements, or you can always write out the electron configuration. And the electrons that are in the highest n value of subshells are your valence electrons. The second concept of bonding is that only certain arrangements of electrons are more stable than other arrangements. So some arrangements of electrons are going to be more stable and therefore more likely than others. And the octet rule, which is what we're going to talk about here, explains why some arrangements of electrons are more stable than other arrangements. So when we say that certain arrangements are more stable than others, stable means an arrangement so that the system doesn't easily undergo spontaneous change, which means it won't easily react. And we know from our trends in the periodic table that noble gases are very stable and do not readily react. They're the most stable elements. They don't undergo very many chemical reactions. We also know from electron configurations that noble gases all have 8 valence electrons, because their S and their P subshells are completely filled. And the S subshell can hold 2 electrons and the P subshell can hold 6. So if they're both totally filled up, the noble gases have 8 valence electrons. So putting these two together, a filled electron orbital or a filled highest principal quantum number of subshells represents a very stable electron arrangement. So if an atom has a completely filled S and P subshells at their highest principal quantum number, their highest energy subshells are completely filled up with electrons, we expect them to be very stable, just like noble gases that have filled S and P subshells are very stable. And because this all involves 8 electrons to fill those S and P subshells, that's where we get the name, the octet rule. 8 means oct, or oct means 8. And so the octet rule is saying that atoms that have 8 electrons filling up their outermost S and P subshells are going to be very stable. And chemistry is moving towards this kind of atoms wanting to form bonds that are going to increase their stability. And so atoms are more likely to form bonds so that at the end of bonding, their electrons are in a more stable electron arrangement, meaning that at the end of bonding, they hopefully have 8 valence electrons since this is a more stable arrangement. And so the octet rule says that when forming compounds, atoms are going to gain, lose, or share electrons to obtain a noble gas-like electron configuration for each of the atoms involved. And when we say a noble gas-like electron configuration, we mean that each atom, when forming a compound, they're going to be gaining, losing, or sharing electrons so that they end up with 8 electrons in their valence shell, so that they fill up their highest energy shell with 8 electrons to get it to the most stable state it can be in. And so we call this a full octet. When an atom fills up its valence shell, its S and its P subshells that are farthest from the nucleus are completely filled up. It'll have an electron configuration that looks just like a noble gas. And again, we call this a full octet. And so when atoms form bonds, they're forming bonds and moving electrons around or sharing electrons to obtain a full octet. So when ions form, what's happening is that atoms are either gaining or losing -1 charges for each electron transferred. And so when an atom gains an electron, it's gaining a -1 charge because electrons are negatively charged. So when an atom gains an electron, it becomes more negatively charged. When an atom loses an electron, It's losing a -1 charge. So it's losing some negative charge, which means the atom becomes more positively charged. And when this happens, you end up forming a positively charged ion. When an atom loses an electron, it loses a negative charge, so it becomes more positive. Or you end up forming a negatively charged ion if an atom gains an electron. And we call positively charged ions cations, and we call negatively charged ions anions. So cation, if something is positively charged when it becomes an ion, and an anion if an atom is negatively charged when it makes an ion. So an ion is just an atom or a group of atoms that is positively or negatively charged due to the gain or loss of electrons. Remember, these atoms are keeping their same identity, so the number of protons inside their nucleus, the number of positive charges isn't changing. The only thing that's changing is how many negative charges they have in terms of the number of electrons. So when an atom gains or loses electrons, it gains or loses negative charge, which then results in the overall atom having a positive or a negative charge. So there's two types of ions, anions and cations. And again, anions are formed when an atom gains electrons to obtain an overall negative charge. And cations are formed when an atom loses electrons to obtain an overall positive charge. So cations are positively charged, and anions have negative charge. Remember, electrons are negatively charged. So an anion is formed if an atom, like chlorine, gains an electron. It gains a negative charge, so it has more negative charge. And a cation is formed if an atom loses an electron. So sodium is giving up a negative charge, which results in it having more protons than electrons, so it has a positive charge overall. So the ion charge, the magnitude of the charge, like how many charges it has, depends on the numbers of electrons that are gained or lost. So if we look at the top example, we look at the exchange of electrons between fluorine and lithium. Lithium has one valence electron, it's in group 1A. It's likely to lose an electron, to give up that one electron. And fluorine has 7 valence electrons. It's in group 7A. It really wants to get to 8 to meet the octet rule. And so fluorine would be happy to accept 1 electron. And so lithium is eager to give up an electron. It just has 1 electron in its valence shell. If it gives up its electron, then its next highest valence shell will be completely filled up. So lithium's eager to give up an electron. Fluorine is eager to accept 1. So when lithium gives up 1 electron, it ends up with a charge of +1. And when fluorine gains 1 electron, it ends up with a charge of -1. So lithium ends up being a cation because it has a positive charge, and fluorine ends up being an anion because it has a negative charge. If we look at another example between magnesium and oxygen, magnesium has 2 valence electrons. It's in group 2A of the periodic table, so it has 2 valence electrons in its outermost shell. It wants to have 8 electrons in its outermost shell. The easiest way for it to get to 8 is to give up these 2 electrons, because once it gives up these 2 electrons, its next most outer shell is going to have 8 electrons in it. So it could either give up 2 electrons, or it could try to take 6 electrons, but it's going to be a lot easier for it to give up 2. That's like the fastest way to get to a full outermost shell. So magnesium is eager to give up 2 electrons or transfer 2 electrons. When it gives up 2 negative charges, it ends up being positively charged, and it has a positive charge of 2+. It gave up 2 negative charges, but it still has the same number of protons. Started out with 12 protons and 12 electrons. And when it gives up 2 electrons, it still has 12 protons and now 10 electrons. If you take +12 and add -10, you end up with +2. So the overall charge on this magnesium cation is 2+. So we end up with a magnesium 2+ cation because it gave up 2 electrons. Oxygen is in group 6A of the periodic table, which means it has 6 valence electrons. So oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6. To get to 8, to meet the octet rule, to have a full octet and be in a more stable state, it needs to gain 2 electrons. So magnesium and oxygen get along great because magnesium is ready to give up 2 to get to a full octet, and oxygen is ready to accept 2 to get to a full octet. So magnesium can transfer its 2 electrons to oxygen. Oxygen gained 2 electrons, so it gained 2 negative charges. So now oxygen has a charge of 2-. And it's an anion because it's negatively charged. So the number of electrons that are given up or gained tells you the charge, like the number of the charge. If electrons are given up, the charge is positive, and the number of electrons that are given up from an element tells you the number of the charge. So if an element gives away 2 electrons, it's going to have a charge of 2+. If an element gives away 3 electrons, it's going to have a charge of 3+. For the anions, if an element gains electrons, it's gaining negative charge, so it's going to make an anion, a negatively charged ion. And the number of charges is the number of electrons that it gained. So if oxygen gains 2 electrons, the charge on that oxygen ion is 2-. If we had something like nitrogen and it gained 3 electrons, the charge would be 3-. So the number for the charge corresponds to the number of electrons that were transferred. And if an atom is giving up electrons, it's going to have a positive charge. And if it's gaining electrons, they're going to have a negative charge. So the octet rule, again, says that atoms tend to gain or lose electrons until they obtain the electron configuration of the closest noble gas. Because noble gases have full outermost electron shells with 8 electrons, other atoms are going to tend to gain or lose electrons through bonding to get to the closest noble gas to be more stable. So if we look at that from an electron configuration standpoint, let's say we look at the electron configuration of sodium. So electron configuration is 1s2, 2s2, 2p6, 3s1. So sodium could gain 7 electrons, and it would have this electron configuration where that rest of its S subshell and the 3p subshell would be filled up. You'd have 8 electrons in its outermost shells, and it would have an electron configuration just like argon, the noble gas. The other way that sodium could get to 8, a full outermost shell, is if it lost 1 electron. If it lost 1 electron, it would now have the electron configuration 1s2, 2s2, 2p6, and it doesn't have any electrons anymore in its 3s orbital because it gave 1 up. And so now if we count its valence electrons, we count them just in the highest principal quantum number shells, which is 2. And so we have 2 in the 2s plus 6 in the 2p equals 8. And so the fastest, kind of most direct way for sodium to get to a full octet is to lose 1 electron instead of gaining 7. And so sodium's full octet looks like the noble gas that came before sodium in the periodic table. So now sodium's electron configuration, 1s2, 2s2, 2p6, the sodium ion, after it lost 1 electron, has the same electron configuration as neon, the preceding noble gas. Because sodium lost 1 electron, it's now Na1+. It has a charge of 1+ because it lost a negative charge when it lost an electron. And we oftentimes, instead of writing the 1, we just write plus. Okay, let's do another one. So we have fluorine. Its electron configuration is 1s2, 2s2, 2p5. So fluorine could gain 1 electron. And its new electron configuration, if it gained 1, would be 1s2, 2s2, 2p6. And if we check that it meets the octet rule, by gaining 1 electron, it added an electron to its 2p5 orbital here, 2p5 turned into 2p6. So it has 8 electrons in its highest energy orbitals. 8 electrons, so it meets the octet rule. The other way that fluorine could meet the octet rule would be if it lost 7 electrons. If fluorine lost 7 electrons, it would now have the electron configuration 1s2, and it wouldn't have any electrons left in its 2s or its 2p orbitals because it's lost 7 electrons. And so it would still meet the octet rule, in this case, the duet rule. Its highest energy shell, the 1s shell, is completely filled with electrons, 2 electrons, but it's not as likely to do that as it is to just gain 1 electron. The fastest way, most direct way to get to a full octet is to gain 1 electron rather than lose 7. And so because of that, fluorine tends to make ions with a -1 charge, F-, because fluorine tends to gain 1 electron to get to a full octet. So there's some guidelines for the gain and loss of electrons from main group elements, some kind of patterns that are followed. So for metal atoms containing 1, 2, or 3 valence electrons, they tend to lose electrons to get to a noble gas-like configuration. So for metals in group 1A, or column 1, or in group 2A, column 2, or in group 3A, column 13, this is just column number here. This is the Roman numeral number. For these metal elements, in order to get to the closest noble gas configuration, elements in group 1A or column 1 are going to tend to lose an electron to have an ion charge of +1. The metals that are in group 2A, column 2, are going to tend to lose 2 electrons and therefore end up with an ion charge of 2+. And metals that are in group 3A, or column 13, it's the one that starts with boron, so aluminum and gallium, those metals, those are going to tend to lose 3 electrons and end up with a charge of 3+. For nonmetals, they tend to contain 5, 6, or 7 valence electrons. So starting from row 17, or column 7A, nitrogen, oxygen, fluorine, they tend to gain electrons to get to the closest noble gas-like configuration. So for elements in group 7A, it's the column that starts with nitrogen, or group 7A, or column 17. Sorry, that's the fluorine column, the halogens. They're going to tend to gain 1 electron. So this is halogens. So your halogens are going to tend to gain 1 electron. And if they gain 1 electron, then they look like the closest noble gas, the noble gas that's just ahead of them in the periodic table, and they tend to have charges then of -1. Moving 1 column to the left, group 6A, or column 16, starts with oxygen. Those elements tend to gain 2 electrons to look like the closest noble gas. So since they gain 2 electrons, they end up with a charge of 2-. And then moving 1 more column over, the one that starts with nitrogen, group 5A, or column 15, those elements tend to gain 3 electrons, so they end up with an ion charge of 3-. If we look at group 4A, which is column 14, these elements in column 14, or group 4A, have a unique position because they're right in the middle of the octet rule. They're in position 4. So starting with carbon, that group on the periodic table, that column, elements in that column could gain 4 electrons to get to a full octet, or they could lose 4 electrons to get to a full octet. One way isn't necessarily automatically easier than the other way. And so they could form ion charges of either plus or minus 4, depending on if they gained 4 electrons to get to a full octet, or if they lost 4 electrons to get to a full octet. The elements in that group, group 14, group 4A, column 14, the ones towards the top of the group, carbon and silicon, they're going to tend to gain 4 electrons to get to a full octet. So carbon, when it forms an ion, would tend to form an ion of 4 minus. As you move down the column into tin and lead are more metallic in nature, so they're going to tend to lose electrons to get to a full octet. So tin and lead would tend to lose electrons and make ions of charges of 4 plus. But because column 4 crosses the metals to non-metals staircase, it has some of both. It's kind of depending on which one you're talking about, whether it tends to gain electrons or lose electrons. Non-metals tend to gain electrons and make negatively charged ions, and metals tend to lose electrons to make positively charged ions. So this is a periodic table that shows the most likely ion charges for the main group elements and some select transition metals. So for the first column of the periodic table, group 1A and hydrogen, the ions of these elements are going to tend to be +1 ions. For group 2A, the ions in this column, starting with beryllium, are going to make ions with a charge of 2 plus. For group 3A, they tend to make ions that are charged 3 plus. And we're specifically highlighting aluminum and gallium here because these are metals. Group 5A, or Roman numeral 5, group 5A, they're going to tend to gain 3 electrons. So if nitrogen starts here with 7 electrons, if it gains 1, 2, 3 electrons, it'll have 10 electrons and look just like the electron configuration of neon. So non-metals in this column are going to tend to gain 3 electrons to look like the closest noble gas. And because they gain 3 electrons, they're going to tend to have ion charges of 3 minus. Elements in group 6A or 16 are going to tend to gain 2 electrons. So if we look at oxygen here, it has 8 electrons as an element. It has 6 electrons in its outermost shell. 1, 2, 3, 4, 5, 6 in its outermost shell. So it needs to gain 2 more electrons to end up having an electron configuration just like neon, the closest noble gas. Halogens, elements in group 7A, column 17, they only need to gain 1 electron to get to the closest noble gas. So because they're gaining 1 electron, they're going to have a charge of -1 as an ion. And then the noble gases already have 8 electrons. They're not going to tend to gain or lose any electrons, which means they're not very reactive. Because chemical reactivity, making and breaking bonds, is based on gaining, losing, or sharing electrons to get to a full octet. And since the noble gases already have a full octet, they don't need to undergo a chemical reaction, making or breaking a bond, in order to get a full octet to be more stable. So let's do a little bit of practice. This is from page 1 of worksheet 2. Worksheet 2 is located in the back of your lab manual. It's the next worksheet that we'll be doing in the lab portion of the class, but it corresponds a lot to what we're talking about in lecture. So we'll do a lot of examples from worksheet 2, and you should start working on that as we go through chapters 4 and 5. So from worksheet 2, page 1, how many electrons would each need to gain or lose to be isoelectric with the nearest noble gas? So how many electrons would each of these elements need to gain or lose to have a full octet? What would their ion charge be? And would it be a cation or an anion? So if we look at the first one, barium. Barium is in group 2A. It's an alkaline earth metal. So alkaline earth metals in group 2A are going to tend to lose 2 electrons. So when barium loses 2 electrons, it's going to make a Ba2 plus, barium 2 plus ion. And this is a cation. The next one's aluminum. Aluminum is located in group 3A or column 13. So it's going to tend to lose 3 electrons. If it loses 3 electrons, it's going to be Al3+, which is a cation. Bromine. Bromine is a halogen. It's in group 7A or 17. So it has 7 valence electrons. So to get to 8, it's going to gain 1 more. And since it's gaining an electron, it's going to have a negative charge added to it. So bromine, when it gains an electron, will be Br-, and that's an anion. Nitrogen. Nitrogen is in group 5A or column 15. To get to 8 electrons, it has 5 valence electrons and it needs to get to 8. It could either lose 5 to look like the previous noble gas, or it could gain 3. So the fastest way to get to 8 is for it to gain 3 electrons. So nitrogen is going to gain 3 electrons and be N3-. And that's an anion. So you'll get some more practice doing this in worksheet 2. On page 1, this is what it wants you to do, to come up with the element, the ion, with the proper symbol to show the charge, and then whether it's a cation or an anion. So concept check. Give the chemical symbol for the ion form when each of the following happens. So when potassium loses 1 electron, the symbol for potassium is K. And if it loses 1 electron, that means its ion is going to have a charge of 1+ because it lost 1 electron. For number 2, sulfur. If sulfur gains 2 electrons, we're going to have the symbol for sulfur, which is an S. And it's gaining 2 electrons, so it's gaining 2 negative charges. So its ion charge will be 2-. Nitrogen gaining 3 electrons. So we have the symbol for nitrogen, N, and it gains 3 electrons. So it gains 3 negative charges since electrons are negatively charged. So N3-. And then challenge yourself to get extra practice with electron configurations and orbital diagrams. Could you write the electron configuration for each of these? And could you draw the electron orbital diagram for each of these? And I just put a note on convention. When writing ion charges, the convention is to write the number that corresponds to the charge and then the positive or the negative sign. So you see here when I wrote nitrogen 3-, I put the 3 first, the number, and then I put the sign. And that's just the convention that's used when writing charges, is you put the number first, the magnitude of the charge, and then you put the sign. So we're next going to talk about what are called isoelectric species. These are atoms or ions that have the same number and configuration of electrons. And so any atoms that have the same number and configuration of electrons are called isoelectric to each other. They're isoelectric species. So for example, if we look at neon, neon's a noble gas. Its atomic number is 10. It has 10 protons in its nucleus, and it has 10 electrons around its nucleus. We're just talking about elemental neon, the noble gas, and its charge is 0 because it has the same number of protons and electrons. So 10 plus 10 - equals 0. It has 10 positive charges from the 10 protons, and it has 10 negative charges from the 10 electrons. And when you add those together, you end up with an overall charge of 0. The electron configuration for neon is 1s2, 2s2, 2p6. So it has 8 valence electrons in its highest energy shell. Its highest energy shell is the n = 2 level, and there's 8 electrons there. 2 + 6 = 8 valence electrons. Now, if we check out the magnesium 2+ ion, we'll see that the magnesium 2+ ion is isoelectric with neon. And that means it has the same number of electrons and it has the same electron configuration. So the magnesium 2+ ion The atomic number of magnesium is 12, which means it has 12 protons in the nucleus. And if we're talking about Mg2+, that means that magnesium lost 2 electrons. So magnesium, the element, would normally have 12 electrons because it would be charged neutral as an element, but the magnesium 2+ ion has 2 fewer electrons. So it only has 10 electrons. It lost 2 electrons. Because it lost 2 electrons, it has a charge of 2+. If we wrote the electron configuration for the magnesium 2+ ion, it would be 1s2, 2s2, 2p6. And that's because it used to have 2 electrons in its 3s orbital, but it lost those 2 electrons, so 3s0. We don't have to include that in its configuration anymore because those electrons aren't there. So you can see magnesium now, magnesium 2+, also has 8 valence electrons, and it has an identical electron configuration to neon. So we would say that neon and the magnesium 2+ ion are isoelectric species. They have the same number of electrons. They both have 10 electrons. Let's make that a check mark. They both have 10 electrons, and they both have the same electron configuration. So that means they're isoelectric to each other. It's important to recognize isoelectric species because as we make ions, right, we're trying to get to the closest noble gas. So if an ion has the correct number of electrons added or subtracted from the element to get it to the closest noble gas, it will have the same electron configuration or be isoelectric as the closest noble gas. So it's a way you can check to make sure that you made the ion properly if you're making an ion from an element. Look for the closest noble gas, write out the electron configuration, and make sure that the electron configuration for your ion matches that of the closest noble gas. So again, isoelectric species are atoms or ions with the same number and configuration of electrons. So an example of what's called an isoelectric series would be a series of atoms that all have the same electron configuration. So an isoelectric series for neon would be all of these elements here. So neon, the noble gas with atomic number 10, has 10 total electrons. 2, 4 plus 6 equals 10 total. It has 8 valence electrons. The N equals 2 level is its highest shell, and there's 8 electrons in that. So that's 8 valence electrons. And so each of these ions also has 8 valence electrons with the same electron configuration, 1s2, 2s2, 2p6. And so because each of these ions exactly matches in terms of the number and location of electrons, exactly matches neon, these are all isoelectric with neon. So for example, if we wrote out the electron configuration for nitrogen 3- would be 1s2, 2s2, 2p6. That's nitrogen 3-. We compare that to nitrogen, the element, without any electrons added. Nitrogen, the element, is 1s2, 2s2, 2p3. And so we added 3 electrons. 2p3 turned into 2p6. We added 3 electrons, hence we got the 3- charge. And now the electron configuration for nitrogen 3- matches the electron configuration for neon. And so nitrogen 3- and neon are isoelectric to each other. And you can check these other ions, oxygen 2-, fluorine-, sodium+, magnesium 2+, and aluminum 3+, are all also isoelectric with neon, meaning they have the exact same electron configuration as neon. So on the next couple slides, I have an exercise, like a practice example, to kind of help better illustrate isoelectric species and give you some practice with them. So what I want you to do is choose a noble gas and write out the electron configuration for that noble gas. And then identify the closest alkali metal, alkaline earth metal, and halogen, the closest to your selected noble gas. And then you'll answer the following questions by filling in the table in the next slide. So what is the electron configuration for each species when isoelectric to the noble gas you selected? How many electrons does each isoelectric species have? How many protons does each isoelectric species have? And what is the ion charge on each species? So this will give you practice writing out electron configurations. This will give you practice adding electrons to the configurations of elements or taking away electrons from the configurations of elements to make ions that are isoelectric to the closest noble gas. Noble gases all have full outermost shells. They fulfill the octet rule. So all of your isoelectric species will have 8 electrons in their outermost shells once they're isoelectric with the noble gas. Isoelectric means they have the same configuration and the same number of electrons. So hopefully in number 2, once you draw your electron configurations and you count up the number of electrons, they should all have the same number of electrons. But because they're different elements, you have an alkali metal, an alkaline earth metal, and a halogen, they're going to have different numbers of protons. And so when you calculate the ion charges, you add up the number of protons, and then you add up the number of negative charges from the number of electrons to get the total ion charge. Your ion charges will be different for each alkaline metal, alkaline earth metal, and halogen. So if we do one as an example, and I highly recommend you do one on your own too, to get practice with this. Let's say my selected noble gas is argon. The electron configuration for argon is 1s2, 2s2, 2p6, 3s2, 3p6. So argon has, in its highest n subshells, which are the n equals 3 subshells, it has 8 valence electrons, which is what we would expect from a noble gas. So we wrote out this configuration most likely correctly, as long as we didn't make any mistakes down in this part. So now I want to pick out the closest alkali metal to argon. So if I look at the periodic table, the closest alkali metal to argon is the alkali metal that's just ahead of argon on the periodic table. I could go backwards to sodium, or I could go one box forward, which is the next row down, to potassium. So I'm going to go one box forward because that's the closest. So potassium would be the closest. The electron configuration for potassium as the isoelectric species, we flip back a slide, the electron configuration as the isoelectric species, we'll just pencil that in, isoelectric, should be exactly the same as the electron configuration for argon. So it should be 1s2, 2s2, 2p6, 3s2, 3p6. So the number of electrons that potassium has is 2, 4, 10, 11, 12, 18 total. The number of protons that potassium has is 19. So if you take positive 19 plus negative 18, because there's 18 electrons and they each have a charge of -1, positive 19 plus negative 18 equals 1 plus. Now, if we look for the closest alkaline earth metal, alkaline earth metals are found in column 2A of the periodic table. So our closest alkaline earth metal is going to be calcium. It's 2 boxes in the periodic table ahead of argon. It's going to have the same isoelectric electron configuration as argon. which means it's going to have 18 electrons, but calcium has 20 protons. So if you take positive 20 plus negative 18, the charge on that calcium ion when it's isoelectric with argon is 2 plus. Now the closest halogen to argon is chlorine. Chlorine is 1 box away from argon, just to the left of it. So when chlorine is isoelectric with argon, it's going to have the same electron configuration. Which means it will also have 18 electrons, but chlorine has 17 protons. So positive 17 plus negative 18 equals 1 minus. So this is how you can figure out the ion charges based on looking at an element and picking out the closest noble gas and making that element isoelectric with the closest noble gas, counting up the number of electrons and comparing that to the number of protons to get the overall ion charge. And again, it's due to the octet rule that elements will try to get to an electron configuration that's like the closest noble gas, because noble gases all have full octets, meaning that their highest energy electron shells are completely filled with electrons, which is a very stable arrangement. And other atoms also want to get to a stable arrangement by bonding, by gaining electrons through an ionic bond or losing electrons due to an ionic bond or sharing electrons due to a covalent bond. To fill up those outermost shells, or in the case of metals, to give up electrons so the previous outermost shell is filled up to get to a more stable state. And that's what facilitates bonding. And that's why some atoms will bond with others readily if their electron shells match up so that it's a nice, easy transition where, say, calcium wants to give up 2 electrons and oxygen wants to gain 2 electrons, and they can easily come together to make that bond. Okay, we're gonna next time talk about Lewis structures for ionic compounds, how to draw the Lewis dot structures, and then based on the Lewis dot structures, bring the Lewis dot structures together for 2 elements, and by combining the dots, fill up the octets, come up with a formula for ionic compounds. All right, thank you for listening. See you next time.